In this video, we discuss about restoring division. For example, take the problem, implement restoring division to divide 12 by 3. See, the binary value of 12 is 1100. Binary value of m is, that is 3, 0011. Take the 2's complement of 3, that is 1101. When we take this value 1100, the MSB is 1 and LSB is 0. This understanding is needed for the following steps. See, now we start the division. Initially we store zeros in A register and the binary value of 12 in Q and the sequence counter is 4. There are 4 bits in the number, so we assign 4. There are 4 cycles or phases in this division. Next we perform shift left operation. When we perform shift left operation, we get this result. All the bits in the A and Q are shifted 1 bit position to the left. Next we have to perform A minus M. Since it is A minus M, that is subtraction, we have to take the 2's complement value of 3 and add with A content. 2's complement value of 3 is 1101. Now add that with the current content of A. So we get the result as 1110. The most significant value of the result is 1. So we have to perform A plus M. So when we perform A plus M, add the binary value of 3 to the A register result or content. So the binary value of 3 is added with the A data, that is A plus M. So now we get the result 0001 and the carry S1. Ignore the carry here. Next step is to decrement the sequence counter. Decrement the sequence counter. Next, we have to repeat all these cycles. So now, as of now, one cycle is over. We already started with the next cycle. So now repeat shift left operation. When we perform shift left operation on Q and A and Q, we get this result. All the bits are shifted 1 bit position to the left. Next is to perform A minus M. A minus M means take the 2's complement value of 3 and add with the A data or A register content. So we get the result as 1 all 4 zeros. That is 1 is the carry and all 4 zeros. So next, in this case, the most significant bit of the result is 0. So we have to replace the least significant bit of Q register with 1. Once again I repeat, we perform A minus M. We get the result as 4 zeros and carry 1. We ignore the carry. And the most significant bit of A minus M is 0. So we have to replace the least significant bit of Q with 1. So the least significant bit of Q is replaced with 1. And then initially that is before the step, the Q value is all 4 zeros. Now the least significant bit of Q is replaced with 1. So and we have to decrement the sequence counter. Now the sequence counter becomes 2. As usual, we have to repeat the same steps. We have to perform shift left operation. So when we perform shift left operation, we get this result. All the bits in A and Q are shifted left. Next we have to perform A minus M. When we perform A minus M, we have to add the 2's complement value of 3 to the A register data. 2's complement value of 3 is 1101. That is added. And we get the result 1101. Here in this result, the most significant bit of the result is 1. Since it is 1, we have to perform A plus M. So when we perform A plus M, we get the result as all zeros and the carry is 1. Ignore the carry. So the next step, we have to decrement the sequence counter. So when we decrement the sequence counter becomes 1. Now we have to repeat the same steps. Perform shift left operation. Then we have to perform A minus M. Then we get the result 1101. Since the most significant bit of the result is 1, we have to perform A plus M. So when we perform A plus M, we get the result as all zeros. And we have to decrement the sequence counter. Now it will become 0. And the Q register content is 0100. So since the sequence counter becomes 0, we have to stop our operation at this position. So the whatever is stored in Q register is the quotient, and whatever is stored in the A register is the remainder. So when we divide 12 by 3, the quotient is 4 and the remainder is 0. So I hope you understand this restoring division method. Thank you. If you like and understand this method, subscribe the videos. Thank you.